I was muted. It always happens. Cool. Hello. I hope music's good there. If it's either too loud or too low, just let me know. It's at 18. I'll just put it at 15. Guess 15 is good. Cool. I love this song. It kind of reminds me of I don't know, like Harry Potter-ish. Movies 5, 6, probably. Haha. Music volume is good. Thank you, 404. Happy to have you here. Bites of Ash. Thank you. Hello. It's perfect. Thank you. Thank you. Thank you. Cool. Okay, first of all, let's see. What's fine tuning? Control C this. It's Quakers and cheese. Hey, Quakers. Cool. There you go. Check in, please, here. Got my energy drink. You'll ask, hey, why an energy drink? PE fellowship started today. So, I had a meeting an hour ago. I have this stream, which is 2 hours. And then just after this one, I have another meeting. So I'm like, I do need this juice. By the way, shout outs to Meta, because this is from Meta. Bully back to back to back. Yes. It's fine though. It's, I have fun. You had my coffee. Yeah. I'm at the point where coffee doesn't do anything to me. It's like, yeah, like that amount of caffeine doesn't do it. I should try pre-workout though. That could probably help. Don't do it though. Don't do it. Which without knowing what fine-tuning is. Don't you worry. That's what we're going to learn. Okay. So let me I'll probably use this layout. Yeah, that's fine. Okay. So stop screen. There we go. Let's start with this. Okay. What is fine tuning? Let me slideshow it first. 2 a.m. still exploring. Hey, I'm happy, even if it's 2 a.m. for you. Thank you that you're watching. If you fall asleep, don't you worry. Cool. Okay, so what is fine tuning by Bully, which is me? So, first of all, a little bit of an introduction about myself. My name is Charbel. Okay, people call me Bully. You can either call me by my name or nickname, both are fine. I majored in robotics and telecommunications engineering. Sorry. I'm from Puebla, Mexico. So yeah. What else? I do love AI a lot. So AI is like what I want to do for the rest of my life. It looks cool, especially in robotics, like drones, autonomous vehicles. It's fun. Like I do really love it. So yeah, part of doing AI is knowing how to fine tune, okay? And this is the perfect time to say this stream is going to fail. Okay, here's the thing. For us to achieve good results, we need to train for some time. That time, yeah, okay, so we'll use YOLO, okay? It takes roughly 2 minutes with the free version tier of the GPU on Colab, like 2 minutes per epoch. Okay, so for 10 epochs, it's 20 minutes. Okay, so I won't train it that long. So I just tried it before. It doesn't achieve good results. Okay, and we'll see why, but just disclaimer, okay? This won't work. You'll have to probably add some more epochs to it for it to work. I won't be staying 20 minutes just waiting, okay? Yeah, sadly. But you'll still have it's uploaded already on GitHub. I'll upload the one that we're going to write after the stream. But yeah, like the one that I'm using as a cheat sheet is already on GitHub. Okay, and my GitHub is, yep, there you go. Cool. Here it is. AI robotics is so fun. Autonomous drone systems, terminators. Yeah, I think that I love automating robots. I have a philosophy of having a failsafe. Okay, like I'm pretty sure we won't get to Terminator part, but I think we should internationally have a code that disables robots and all of them should, like obey that code. Okay, not by voice. Should be like an electromagnetic code, right? Like a Wi-Fi sent code. Okay. It's difficult because someone could hack your product. I don't know. You could have like I don't know, like an autonomous Uber robot, and someone hacks it with that code specifically, because it should be the same code for everyone, because it's international code. But you know what? I think we can figure it out. But yeah, I believe we should do it. Okay, I do it for my drones. So I've automated some drones, and all of them obey a command of whatever you're doing. I don't care. Go down, right? Like, I don't care if you're flying. I don't care what command you have. This command supersedes all of them, and you have to land now. Okay, for safety reasons, we always have it. Okay, cool. Our robotics lab will work. We'll start next week. Cool. Good luck. Nice. Okay, so after the disclaimer that this won't work, let's take a look at what is fine-tuning. So let's probably go back to what fine-tuning means. Okay, I'll take some time, and I know 404 and Quakers already saw this, and some of you, like, I think there are others too there that were in my past stream about what is a neural network. We'll just take a look quickly at what it is again, so for everyone to understand, and we'll go from there. Okay, so a neural network is a machine learning model inspired by the human brain. Okay, probably not by the human brain, but by the brain of mammals, I'd say. Okay, so they have neurons. We have neurons. Each neuron fires up, okay, with electricity and sends signals. Those signals are connected to each other, creating a network, okay, with an input and an output. Okay, I put this same example last time, which is invisible now. I have a cup. Okay, this is my cup. My eyes are the input, so I get the input into my eyes. I compute in my brain. Some neurons fire or turn on more than other neurons. Okay. Does the song have whisper? Is it just me? I'm not sure. I don't know. I think it does, though. I think it has a whisper. But yeah, so my brain computes and it outputs a word. In this case, cup. If my brain were to be badly tuned, I would say this is a flower, which is not. Okay. Someone, life, trained me or my brain to say this is a cup. Okay. That's what the training is all about. If I get, I don't know, this little box here, I wouldn't say this is a cup. Even if it's probably the same color, my brain is smart enough to realize that the shape, color, size, and functionality doesn't mean this is a cup. Okay, that's with training. Okay, so it's made up of layers, interconnected nodes of neurons. Okay, so we have a lot. We can have 10, we can have thousands. Okay, each neuron processes an input and passes the output to the next layer. Okay, so that's math magic that we won't be diving into. We dove into last stream. We won't do it this time. Okay, we'll just superficially see how it works. It's used for tasks like image recognition, language translation, and more. Okay, that's how it is. Okay, cool. So I'll just share with you how this works. Okay, so let me add this thing over here in neural networks intro. I think this is it. What? Maybe, who knows? Okay, cool. So I'll try to run this for now. Let's see, give me a second. Yeah, okay. Come on, connect. Okay, so this is Google Colab. Okay, so while it connects, it's a Jupyter notebook server, but run by Google. Okay, the good thing about this is that it connects to Drive, which I love, and it has some other products such as Gemini to help you, and it has really good GPUs. Okay, in this case, because I'm not paying for it, then like, hey, Google, you can sponsor me. I'd be happy, okay? If you click on change runtime type, in this case, I have the T4 GPU, okay, which is the cheapest GPU that they have. You could get an A100 or an L4, okay? Based on the GPU, it could be faster or like it would change, okay? We'll use we'll use T4, which is a Tesla 4. Yeah, hashtag Bully sponsor, Google sponsor Bully, please. Google, you heard me. Yeah. Okay, so first of all, this one, by the way, is on my GitHub too. Okay, so you can find it there. We'll just take a look at it pretty quick. I have to upload something called a Kaggle. Where is my Kaggle? There we go. Shoot, there we go. So this JSON, okay, connects to my Kaggle or allows me to connect to my Kaggle account. Okay, and I can download datasets from there. Okay, cool. Now, let's see how this works. So I'll runtime run all, and I'll go one by one. Okay, so import TensorFlow as TF means I want to use TensorFlow, which is a framework by Google to use neural networks. Okay, in Python and JavaScript works too. Use Python, don't use JavaScript. Okay, cool. Like Google, what the heck? Like, what would you do to add it into JavaScript? But yeah, JavaScript's not made for numbers. But yeah, anyway, the important part is here. Okay, so we are using a cat and dog dataset. Okay, and from here we say I just created this function that says, hey, give me a random image from the training folder. Okay, so in this case, there's a cat. Okay, that's a cat. We know it's a cat because our brain was trained to say that's a cat. Okay, think about it. Just take a look at the image and say, what is it specifically that makes you think that's a cat? So imagine that you wouldn't see the face. You'd probably say, hey, that's a cat because I look at the paws and that's a cat's paw. But let's just assume you just see this part over here. You probably would struggle. Okay, because there is no detail regarding or telling you, hey, that's a cat. Okay, so you could say that's a dog, that's a pup, that's a fox. Okay, you wouldn't know. Okay, so that's an important thing. Neural networks check for details. Okay, if you were to add a lot of noise to your images, you would lose details. Well, or the way around. If you add noise to enhance the details, that would be better. Okay, and we'll take a look at that. But yeah, here's something called a data generator, which we flow from the directory. That's this directory over here. We say, hey, this is the batch size, the image size, binary because it's either 0 cat or 1 dog. Okay, cool. The seed is just for if you want to do the same thing, it should happen the same thing. Like random numbers should be generated the same if you have a seed. Okay. And this is the neural network. Okay, this is how it looks. Okay, so let's go one by one. We have a convolutional layer. Okay, so this is a convolutional neural network used for image detection. Okay, image, in this case, image classification. Okay, we have two convolutional layers. Okay, we have a max pool. We have another convolutional layer, max pool, flatten, and then we have an output layer. Okay, actually, should be one. There. So here, this is how it looks. Okay. I get the input, which is 256 by 256 by 3. That's called a tensor. Okay, why? Because it's not a matrix by itself, it's a matrix of 3. Okay, so that cube it's like a cube. Okay, so you cannot visualize it. Okay, it's more than we can visualize because it's a dimension ahead from us. Okay, but it's called a tensor because it's like in the same part. You have like 3 matrices. Okay, so I called it a matrix of matrices, and that's a tensor. Okay, I guess it's like the easiest way to think about it. Okay, it's like a matrix of matrices. Okay, it's a higher dimension matrix. Okay, cool. Now, from there, we say, hey, I want these types of images. Get the convolutional layer. I want to have a kernel of 1 on 1. 64 neurons, 128 neurons, 64 neurons, and 1 neuron. Okay, these are called activation functions. Okay, the functions that say, hey, this specific neuron should turn on 2%, 5%, probably 90%, okay? Depending on the image that passes, okay? Because each neuron will keep track of details, okay? How it happens, math magic, okay? Let's just leave it as math magic, okay? Cool. Now, we compile, we say, hey, Mr. Model, I want you to be created with a loss function, an optimizer with a learning rate. This is the speed that the network will learn, okay? So the weights and the biases, yeah, will change depending on this alpha rate, okay, which is called the learning rate, okay? And we train, okay? So while I was explaining, it was training, and you can see here it says accuracy, 53%. It means it's just guessing, okay? For now, it guesses. It says, hey, this is probably a dog, because it doesn't know anything. For 35 seconds, for 250 images, it guessed. Then we can see a 65% increase here, 65 again, 68, 70, 75. It went back to 72, 90%, that was really good, 74%, 75%. Okay, from there, I just created a function to get an image from a URL. Voila. So now you know this is a cat. This is a cat, and this is the probability that the neural network output it. Okay. Yes and no. So that's a really good question. That training said, I don't know how many images does it have, but let's try to scroll it down. It's like, it has like 1,000. Yeah, so we can see 1,096. Okay, so that's a good question. That's called batching. Okay, so batching means I don't want you to load all of the images at once. Just load, in this case, 250 images. Okay, so those images are loaded into RAM. Okay, the more images, the more data you want to load into training, the more RAM you have to have. Okay, and the slower the training goes. Okay, so it takes 250 images, adds them, then it takes the next 250 and adds them. Okay, that's how it works. Cool, nice, good question though. And then voila, that's how it does. Okay, and let's take a look at with a dog. Okay, so I'm gonna do dog image. Pretty quick. Let's see if it gets it wrong or right. This is a cute puppy. Open new tab. I know you're not seeing anything. Wait a second. It should be this one. Yeah. And let's check here. Okay. So if we do this, voila. Okay. Ah, shoot. See? Okay. That's a dog. It says this is a cat. It's actually quite unsure because if it were to be 50%, it would be a dog. So under 50%, if the number is 47 or 49 to 0, it means the model thinks it's a cat. What details it is speaking on, I'm not sure. Could be the pointy ears, the color, the paws, I'm not sure. Okay, so this neural network is pretty simple. Okay, and here's the catch. Okay, this is a neural network that I created. Okay, with the zero experience that I have some experience. With the experience that I have, I created this one knowing how it should go, okay? And it worked somewhat fine, okay? Now, if you were to say, hey, I wanna use a model for a drone, or actually for an autonomous vehicle, okay? Let's call it a car, okay? Should I create my own model? Answer is no. Okay, that would take you ages, right? Like you would have to research, you would have to have a lot of knowledge in creating neural networks. Okay, and that's just not right. There are lots of neural networks out there that you can use. Okay, and you can actually train, and that's called fine-tuning. Okay, so I got the question here. Watching without knowing what's fine-tuning, well, that's basically it. A model such as YOLO, which means you only look once, is trained over probably millions of images, okay? From different types, okay? Let's actually see it here, okay? YOLO neural network, let's see. let's see if I could get here. Okay, let me remove this one for now. This is YOLO. Okay, the one that will be using, wait a second, because for some reason StreamYard doesn't allow me to. Okay, it's taking a moment to load. Wait a second. Oh, come on. There we go. Cool. So this is YOLO. Okay, this is how it looks. Okay, so we have all of these layers. It has 8,732 just in this part over here. Okay, it's ginormous. Okay, it's really, really, really complex, and it does really good. Okay, so what? Wait a second. I just lost connection. There you go. So this is how it looks. Okay, if you say, hey, look at that, it says person, here's a dog, and here's a horse. So it's trained over a lot of data. Probably, mostly, some of them you won't use. Okay, so if you're training for, I don't know, for an autonomous vehicle, you don't care if it's a cow or not. It's just something, right? The more things the neural network knows, the least accurate it could be, and the more time and complex it gets, so the more resources you take to use it. Okay, so you'll need more powerful GPUs, hence you'll need powerful CPUs, hence you'll need a lot of energy, hence you'll need a very, very, very expensive warehouse to actually use that. Okay, that's what happens with OpenAI. Okay, they have just a big model, and they use a lot of infrastructure to maintain it. Okay, so the least the neural network knows, the better, but at the same time, you want it to know a lot. Okay, that's how it is. Okay, so it, yeah, I think that's all for now. Let's go into our fine tuning. There we go. That should be it at this stage. Okay, cool. So, my bad. There you go. So that's a neural network. You just saw how it works. We won't go into the math deeply, but what are weights and biases? Okay, what does that mean? Weights are numerical values that determine the strength of the connection between neurons. Okay, so going back to this image over here, you can see that there is a connection between this neuron and this one. This connection is held up by a number. That number is called the weight. Okay, so the weight, remember activation functions, the weight manages the activation functions to either light up a lot or not a lot, and the output is changed. Okay, so that's a weight. A bias is just a value added. So for all of the weights, we have one bias of a neuron to allow the model to better fit the data. Okay, it's just another number. Okay, together they help the network make accurate predictions. Okay, we as engineers, we want to tweak the weights and the biases. That's what you do when you train. When we are fine-tuning, what we want to do is tweak the weights of the biases of some of the layers. Okay, if you want to retrain the whole model, it's okay. To fine-tune, you don't need to do that. Okay, cool. Now, what is fine-tuning? Well, fine-tuning means adjusting the pre-trained neural network on a new, smaller dataset. Okay, so we say, hey, YOLO knows a lot of things. From all of those things, I want you to focus on, I don't know, in this case, a llama. Okay, so I want you to focus only on animals. Okay, I don't care if you see a car, a plane, a wall, a rock. I want you just to focus on some dataset. Okay, that dataset, you have to provide it to the neural network. Okay, that's the way you say, hey, I want you to think about only this thing. Okay, instead of training from scratch, we reuse the knowledge from a model trained on larger data. In this case, like ImageNet. Okay, cool. Now, it saves, why would you do fine tuning? Like, what's the difference between me creating my own model, not using someone else's model, and training it? Okay, first of all, it saves time and computational resources. You'll need a lot of time to create a model. you'll need a lot of time and resources to get those data sets and then train it. Training takes a lot of time. Okay, so why not just fine tune and reuse the models that exist? Okay, enables models to adapt to specific tasks like medical images, industrial defects, etc. Okay, you could use YOLO for lots of things and YOLO still the same. Okay, cool. So part of fine tuning, you'll need a dataset. Sometimes data is scarce. Okay, it's not cheap. Okay, it's not easy to find. So what do? Take images and you add some noise. So what is noising? Noising is adding random variations into pixel values. Okay, changing the color of the image, rotating the image, flipping the image. We'll add some noise later. Okay, but what it does, it confuses the model a little bit. It reduces the accuracy, but the model trains in better ways. Okay, so a cup doesn't have to be like mine, black and with a plastic over it. If we add some image noising, then we might know, hey, there's probably a blue cup. A blue cup can be larger, smaller, wider. It depends. Okay, that's what noising takes care of. Okay, and more robust training data. Okay, you have more data to train. Let's go. Okay, cool. Now let me stop the screening for now. Wait a second. I should use this one. Yeah, this is the one that I'll use. Okay, and fine tune. There we go. This is the one. Okay. Share screen. Fine tune stream. Yeah, there we go. Cool. Okay, can you see this? Oh, I don't want you to see it like that. Wait a second. Can I do that? Yeah. Okay, cool. And I'll do. Wait a second. Give me a second. I'll have to move this one here because for some reason the iPad doesn't like Google Colab. So I'm like, what? There you go. And I should probably do this thing over here. Better? Yeah, that's better. Okay, cool. So now, thank you, Gemini. There you go. Cool. So first things first, okay? We won't create the model. The model won't be ours. It will be YOLO. How do you download YOLO? Okay, I guess there are lots of ways. This is the one that I use. Okay, if you're not familiar with Google Colab, if you use an exclamation point, it means I want to use bash. Okay, so pip install ultralytics. There we go. Okay, so let me just get a GPU. There we go. We need a GPU for this one. Okay, you absolutely need a GPU for that one. Yeah, if you're not paying, you should only have one. Get rid of this one. Yeah, there you go. Cool. Now reconnect. If you don't have a GPU, what would happen? One, it would take too much time, like insane amount of time, and two, some models don't work on CPUs. They work only on GPUs. Okay, cool. Once we have that, we run this. It'll take like 1 minute or two. There we go. It's downloading something, okay? Some NVIDIA thingies to talk to the GPU. Okay, in the meantime, how do you import YOLO? So we do from Ultralytics, YOLO capital letters, okay? It's marked as an error now because it hasn't downloaded yet, but yeah. So model equals YOLO, and we have here an interesting thing, okay? Sorry, YOLO, it's version 8.nano. It's actually nano.pt. Okay, what is this? Like, what is this? Is it the version of YOLO? What is this? This stands for YOLO. It's a version 8 of Nano. Okay, so you have bigger models of YOLO, more to train, more computational resources, more accuracy. It depends on what you need. Okay, PT is basically a file that stores weights and biases. Okay, so you're storing how the weights and the biases were tuned, and basically you are freezing the model. Okay, that's what they do. They freeze a model, and those biases should, let's say, should react the same in any computer. Okay, it doesn't matter if they have GPU, like the type of GPUs. The weights and the biases basically say, hey, this is how you should react to this certain images. Okay, so we are downloading pre-trained weights and biases, okay, that we will play with in a second. Okay, and let me upload a picture here called Science. Okay, there we go, that's this one. Okay, it's taking some time. Yeah, there you go. Did it crash? No, it didn't crash. Did I click on what? Yeah, wait a second, Science. Is it not? What? It's weird. I don't have. Shoot, wait a second. This doesn't work. If I do result the equals model. Oh, there you go. It was like bugged a little bit. Okay, model. Let's do / content and science that PNG. Okay. You can look for signs like road signs on the internet. Just like download the one that you like. We are going to focus on speed signs. Okay, so come on, signs. There we go. That should be the terminal. Just weird. Wait a second. No, I don't want to analyze. What? Again, it's not doing anything. What? Shoot, wait a second. I'm sorry about that. Restart, disconnect and delete. Yeah, we'll have to do the whole thing again. It happens. Like, yeah. Okay, there we go. I think it works now. We have to rerun the whole thing. We'll wait a little bit, but yeah. Signs, there we go. There you go. Yeah, that's the warning that I wanted. There we go. That's the signs. Cool. So, again, what is this doing? Downloading the weights and the biases of a pre-trained model of YOLO. We want to see what YOLO sees in this sign images. Okay, so we'll run this, wait for it to download, and it'll result, like the results will be stored here. Okay, we have to tweak a little bit for us to see it. Okay, so let's do that. Import for Google Colab, try to use Matplotlib. It works really well. Okay, import matplotlib.pyplot as plt, and then plt.imshow result and 0. Okay, because results is not just it's not just the image, it's the bounding boxes. Okay, which I'll explain in a second. Dot plot. My bad. There we go. Okay, let's just wait for Ultralytics to download. Like if Ultralytics takes this much time to download, training YOLO takes more time. That's why this stream will be a fail. Okay, like it won't work, but at least you know how to fine tune and how to read whatever the model is outputting to you. Okay, come on, Mr. Ultralytics. Okay, there we go. Cool. Now it's downloading YOLO. We'll store YOLO as this version, and there we go. Cool. It's called prediction. Okay, it's predicting. Voila. And again, results. There we go. Sorry, let me just silence my phone. There you go. Cool. So you can see this is the image. Okay. It has a bounding box in the stop sign. You'd say, hey, why just the stop sign? Like, why doesn't it have a bounding box on this sign over here, which I don't know what it means? Like the bike side over here. Because YOLO was trained on images that do not involve any single image of this kind. Okay, so let's say I'm building some robot to say, hey, that's a stop sign, that's a yield sign, that's a taxi sign. and yet YOLO doesn't do the trick now. It doesn't mean that YOLO cannot do it. It means we have to train YOLO to do it. Okay, cool. So in this case, you can see stop sign 0.59%. Okay, it's not so sure. Now, you can see this is red and this is blue, should be all the way around because I didn't fix it. It should be BGR. Okay, so it's output stuff in BGR, which is blue, green, red instead of RGB, red, green, blue. Okay, so it switched the colors. Okay, the colors don't matter. Okay, it's just the output. Okay, cool. Now, as before, we have to create make directory. Okay, in squiggly line, which how do you do a squiggly line? I'm not sure. But this squiggly line over here /dot Kaggle. Okay, we want to use a Kaggle dataset. This is the way to do it. Okay, and then we say, hey, Mr. Collab. Okay, copy Kaggle.json into this part over here. Okay, slash, and then we say chmod, which means give permissions. 600 is execute. I guess it's like read and write or read and execute, something like that. Okay. Into Kaggle. Kaggle. There we go. Cool. And then we do this Kaggle, and then we go into datasets. Okay, because we want to download a dataset. Download -d. Okay, and it's pkdarabi/car detection. That's the name of the dataset. Okay, for that, before I run this, you have to upload your Kaggle JSON file, which is basically a key that allows you to use the datasets. It doesn't cost at all. It's all free, but you have to have a Kaggle account. Okay, cool. So there's my Kaggle JSON. I run this. There we go. Cool. Now we have the dataset. Okay. Now it's in a zip file. You can see it's here. There we go. It's car detection. Okay. So let's import zip file, and as always, zip reference equals zip file. That zip file. Careful with the capital letters there. And here in string, you click on here and you say copy path, paste it here, voila. And now zipref dot extract all. Where? Into content. Content is good, okay? Content is actually here. Okay, so you can see it. Cool. And then zipref dot load. Okay, that should do the trick for now. Let's see. Cool. You can see there's a car here. Test, train, validation. Okay, cool. Worked fine. Let's get rid of this. Cool. So, before you do any training, because you're working with a neural network that's already pre-trained, that you know that it works, so there's a certain guarantee that it works. The neural network could be the best one in the world. If your data is wrong, your neural networks will be wrong. Okay, it doesn't matter if it's the best out of the best, you have to check your data. Okay, so let's do that very quick. Let's do import, come on, import OS. Import environment. Cool. Okay. We check and see with a folder validation for now. What do we want? Okay, we add this one because we'll be using this one to predict to see. Okay, and model equals for now YOLO, basically this one. So the same weights and biases, okay? If we don't change this, then it will use the first YOLO, okay? Cool. So let's see, image folder equals f string such content such car such folder here images. And you can see if we go to content car folder, which should be valid in this case, so we click on valid, we have images and labels. Okay, the labels say, hey, what does this look? This says this is the ID. Okay, 7 could be a car, could be something. Okay, I don't know what it is. Here are some coordinates, x coordinates, y coordinates of the bounding box, and these two I'm not sure what they were. Basically metadata of saying, hey, there's a bounding box, this is the label that it should have. Okay, cool. Now how can I get rid of this? Close that. There you go. Cool. So we're accessing the images only, and in this case label folder equals the same thing. It's an f string of such content such car, okay, slash folder again, and then slash labels. Okay, cool. So now get a random image from the folder. Okay, so we get a number. We get from it the length of OS that list there, because I don't know how many images there are. Image folder. There we go. List. There was a dot there. There we go. Now random equals random dot rand. Oh, come on. Randint. From 0 all the way up to num minus 1. Okay, because we want to get a number, an index number. We cannot get the number itself. If there's 1,000 images, we should get number 999, not 1,000. Just because if we get 1,000, we're out of bounds. Okay, cool. And now image equals OS dot list there. It's image folder in the random number. Okay, so random image. There we go. We don't want to predict, so if not predict, then we just display the image. Okay, cool. So PLT im show should be PLT the im read. Okay, so we read the image from PLT. F string should be the image folder. Okay, slash image name. Okay, voila, that should do the trick. And let's print the label. Okay, so we know what it is. Okay, F image folder. Actually, let's print the name. Folder slash image. And there you go. Cool. Shoot. Cool. Now, else, like if we want to train, or we want to see what the model is looking at, if not image, if we don't have an image here, then what? Wait a second. This is just the weirdest else statement ever. Why did I write this? Was I drunk? If not image, else model image. What? Oh yeah, got it. Okay. So if we say actually if image, if not this image, okay? Yeah, I got it wrong here. I don't know how it worked, but it worked. Okay, if not image, then result equals model. Remember, this is how we predict, okay? Model and then the image, okay? So model, was I drunk? You know what? Sometimes I write some code, then I later read and I'm like, was that me? Like, what? Who, like, this is the worst code that I've written, and it's mine. Okay, so it usually happens. Like, it's my code, and I'm like, why did I write this? Like, I could have done 3 lines instead of 10. I just went for the high mile, like 10. Sometimes happens. That's awesome. Yeah, I probably was drunk. Like, I don't know. And it worked. Like, probably Colab was drunk too. But yeah. Model. Okay. And then we do an f string here. We want to get the image slash image. Okay. Like it's image folder. Cool. And then plt.imshow. This is just to check the data. Result dot in zero dot plot. Okay, this is everything Ultralytics YOLO. Okay, cool. Else, you know, it could be don't drink and drive, don't drink and drive. Yeah, don't do math when you're drunk. Funny story. Yeah, you could do math when you're drunk. I've been told. Cool. Okay. Model image here, and then plt.imshow. There we go. And then result in zero dot plot. Okay. If we want to predict and we don't have an image, yeah. Okay. So we can either predict with a random image or, sorry, with our image or a random image. Okay, that's what it does. Okay, cool. Now, run this, should be fine. So let's do it, okay? Not changing anything from here. Let's just check our data, okay? Check and see. Let's run it. Ooh, okay. So this is something. Okay, this is basically a sine of 20 kilometers per hour. Doesn't look that good, okay? Another one. Oh, there's a 70 there. Okay. So for each image, we have the labels, which are a bounding box coordinates. Okay. Length, width. I remembered. Length and width are the other 2 numbers that were in the labels part. We have x and y coordinates in the label. Okay. So let's do one more. There's a stop sign. There's looks like 60. I'm not sure. Well, that looks like 120. Yeah. So you can see the data is not that good. Okay, so it'll be a little bit difficult for the model to actually learn. Okay, that was done on purpose. Okay, so I want the model to fail. Okay, it will fail. That's what we want. See, that's a 40 there, but it has some things. So see, you have to always check your data. Okay, cool. Now, we have to save our weights. We will train models. We want to save the weights so that we can use them later. Let's say that some weights are actually usable. You have to save them. Okay, if not, they just go away. Okay, save weights from the results. Okay, so we do save there equals results dot save there. Okay, so we get the directory best weight path equals the f string, and I'll show how this works in a second. Save there. Okay, slash weight slash best dot pt. Okay, and then return best weight path. There we go. Cool. So what does it do? How does this work? Ultralytics YOLO by itself saves, okay, someone, whoever did it, thank you. Google sponsored that person too. Okay, hashtag. Made a function that it saves the best weights when training YOLO. Okay, so we can get access to it via this part over here. So per each run of YOLO, we get a new folder here. Okay, and we can get the best weights from there. Okay, that's what it does. Okay, cool. Now let's it'll run without issue. Let's start. Okay, fine tune number 1. Let's put it here. Fine tune number 1. Okay, and let's do this a title. There we go. So we'll fine tune. Okay, cool. We can do result one. You know, just using the dataset without doing anything, okay? Equals model, the train, okay? I'll do data equals content slash content means folder, okay? Car slash data.yml. What data.yml? Each model understands datasets its own way. YOLO understands the data using data.yaml, okay? It says train, validation, tests, and see its number of classes. Here are the names of the classes, and this is just RoboFlow stuff. Okay, this is what YOLO understands. If you want to create a dataset for YOLO, this is the way to do it. Okay, cool. Oh shoot, my bad. We can do this. Okay, we add something. Oh, come on! What's happening? Okay, we add some things called epochs. Okay, I'll do, again, this is doomed to fail, okay, because we don't have enough time to train it for longer. I'll do 2 epochs. Okay, it won't work. Let's just experiment, okay? Image size equals 640 pixels, okay? The longer or the bigger the image, the more time it takes, but the more details it sees. Okay, got it? Cool. Okay. And we will name this run fine tune 1. Let's run it. Ooh, thank you. Thank you, Mr. Error. Content. What? Can copy the path here, probably. Was that out? There we go. Cool. So it's training. Now it says, hey, here are the parameters. Here's whatever I'm going to train. Okay. And now it's doing its own thing. Okay. Is it possible to fine tune Flux using Colab? Also, we'll look at the script emailed after the stream. It's on my GitHub. Okay, you can look for it. It's in Bully 1601. Okay, that's my GitHub user. And are we using an external APIs for this? Yeah, we are using, so if by API, so no API, we're just using Ultralytics, okay, which is not an API, it's just it's an API. Yeah, let's call it an API, okay, because you can access lots of models online, okay. But yeah, you can use RoboFlow too, like the page of RoboFlow. You can go in and like interactively train a model. I love to see the code. Okay, I think you can learn more by looking at the code. Okay, cool. So you can see it's still on the epoch 1. Okay, so it'll take. There it is. It's taking a minute now. It takes like 2 minutes. Okay, or like a minute and a half. Okay, I got Color Enterprise. Ooh, you got the good one. Oh yeah, for sure. You can train LoRa using Colab. Yeah, for sure. And you have GPUs like way too powerful. So yeah, for sure. Okay, there's epoch 2. Let's take a look at something interesting. You can see the loss is pretty high here. It means there is a lot of error. Okay, and you can see here it's going down. Okay, so YOLO is actually learning. Okay, so there's no doubt that YOLO learns. Now the thing is, we need more epochs for it to learn. You can actually see box loss. It's where the box should be, and it's high. It's not that bad at this one. Okay, cool. Now it takes some time. That's why we can't wait a lot. But let's see, do you have something for that on your GitHub, or where should I look on the basic LoRa? No, I don't have anything for LoRa. Okay, try to look on LoRa's. Okay, let's see if I can find something here pretty quick. LoRa Can you use ultralytics with LoRa? I'm not sure. Yeah, okay, so this is something that Medium always have lots of interesting things. Okay, so just found this, okay, online. Medium is really good. Okay, try that. Okay, I don't use LLMs that much, but you could try that. Okay, and yeah, you can use, like, I've used Colab for LLMs once. Okay, and it works just fine. I trained Gemma, which is like a Gemini version of, like a Gemini variable of Gemini, from Google. Okay, so I'd use Gemma too. Cool. Okay, so this is finished. If we go to runs, we go to, I said runs, sir. Oh, come on. Okay, there we go. Detect, fine tune 1. Okay, and you have here weights. Oh, it's fine tune 1 too. Okay, so it's weights. We have lots of things here, interesting things. Let me just remove this one. We have some curves here, a confusion matrix that we'll take a look at. And we have here the best thing, which is, where is it? Where did we say it was? Wait a second. It's in weights. Yep, best. Oh, here, weights, best. Okay, so we have the last weights recorded and the best weight recorded. In this case, should be this one, right? Should be the last one, because you can see the loss, either the box loss, is way less. Okay, if you are working with 200 epochs, some epochs might be better than other ones. Best.pt keeps track of that. Okay, so you have it there. What is the purpose of the Ultralytics package? And it requires any API keys? Okay, so it doesn't require any API keys. You can just download it. And Ultralytics basically offers you a lot of models, including YOLO, for you to use. Okay, and some pre-trained weights. Okay, so we leverage Ultralytics by using YOLO. Okay, 100% free, no API keys. Cool. Okay, so yeah, now let's take a look at some valuable information that we have from the runs. Okay. Let's see, I'll do that one later. Okay, I'll do that one later. Cool. Now, let's save this weight, okay? Save the weights. We do best 1 equals save weights. Which weights? Result should 1. There we go. So we save those weights, and now we can predict, okay? Predict using those first. Cool. I'll just get rid of this. So we do check and see the function that we before, like previously wrote. Check and see. The only thing that will change is predict equals true, and model equals YOLO. Okay, the same YOLO object, but now we'll use best 1. That best 1 is a PT file of your best weights from here. As easy as that. Okay, and our image will be our science image. Okay, content science.jpg. Okay, now come on, results 1. What the image is going to say here? What did I wait a second? I just messed something up. Give me a second. I see a question there. Give me a second. Let me just save. Where's save? Oh yeah, it happens. It always happens. There it is. Save there. Results. Did I? Yeah, that's save there. Huh. Okay. And it says, wait a second. This should work. So it's not a module. So it's a what? Is it a function? I don't think so. Let's see. Could it be a function and I just messed things up there. Nope, it's not a function. What? That's really weird. This should work. Okay, result.saved here. Okay, results. Let me just quickly check, because if not, then we'll have a problem. The results should be here. Tell you to use Claude. Well, probably. No. We can figure it out. Wait a second. Okay, it's not weights. FRPR, arcs, confusion matrix. No, not labels. Results. No. What? Wait a second. I know why. Because for some reason, this one over here, this one over here bugs. Okay, I guess it's because it's the first one. It happened to me. I just remembered. So we have to manually do this. So it's fine tune 1, 2. For some reason, it works for the others. It doesn't work for number 1. I don't know why. Okay, so we do this, 1, 2. Okay, give me a second. Oh, come on. Fine tune 1, 2 dot pt. Or actually, it should be this one. Wait a second. Should get this one. This best pt. Copy path. There you go. That should do the trick. Oh, come on! String has got to not saved here. What? Oh, yeah. Wait a second. Best. It should be the best PT, and we are trying to access it through this part over here. Results 1. Let's do 1, 2. 1, 3. Okay, just for sake of argument. Yeah, because this, I remember this bug. You see fine tune 1, 2 and fine tune 1. It doesn't make sense. I don't know why. Okay, cool. Time for questions in the meantime. This should, wait a second. This should be results. Cool. And after that, yeah, there you go. Cool. Okay, so how many steps? Okay, wait a second. We have a lot of questions. What purpose of auto? Okay, that's good. How many steps are we using to train right now? And how many do you suggest usually? Oof. Okay, if I had enough time, 50 to 100. Okay, it'll take a lot of time. Yes, what I do is I leave Cole up there, I go eat or do something else, and then come back. Okay, 100 epochs should do the trick. I'm using 2 right now, so you can see here it says epochs 2. Okay, because it takes 1.5 minutes approximately per epoch. So yeah, it's a lot of time. We use 100 epochs, it'd be 100 minutes. Okay, time to use Claude. No, in this case, no. I've never used Claude before. I think Chad does the trick good. They say Claude is very good for programming. Never used Claude before. What's the purpose of Kaggle.json? That's a really good question. So if you see here, before we accessed this dataset from Kaggle. Okay. For us to have access to that Kaggle dataset, we need a Kaggle.json, which is like your API key for Kaggle. Okay, so Kaggle knows you're not a bot trying to, just use datasets at random. So you have to do all of this, and you go into your profile in Kaggle, click on create API key, and voila, it gives you the Kaggle JSON. You upload it here, you do the math here, and voila, you have your dataset. Okay, cool. Now it's executing. Come on, you can do it. You can see actually the spike of RAM here. It means all of the images just now were downloaded. Okay, were loaded into RAM. Okay, yeah, I don't like Kaggle. Like the Kaggle interface is not that good. The notebooks are just Colab is the go-to. Like Colab is the go-to. Cool. Nice. Okay, let's just get rid of this. Wait for it to train. See that it takes a lot of time. It gets a summary. Okay. There we go, come on. Yep, and this should work now. Okay, in the meantime. Oh, come on! Really? Is it called results 1? Results 1. What the heck is going on? No way, why? Fine tune 1.3. Yeah, that's results 1, yeah. This is just weird. results one. Give me a second. If not, then we'll just skip this part over here. But yeah, fine tune 1.3. Here it is. What's happening? Did I miss something? Wait a second. Come on. I said this was going to be a fail, not a failed stream. Wait a second. Yep. And then results one, and then we go results one here. Wait a second, let me check my cheat sheet. Save weights. Yep. Let me do something here. I'll try to copy this. If not, we won't save the weights. I think it doesn't affect at all. Okay. Where's our save weights? There we go. Just in case, let's see if that works. I don't think so. Yeah, no, it's not working. For some reason, I thought it should save here. This is just weird. It should have. This is just weird. Okay, cool. We won't be able to test it visually. Okay, that's not good. I kind of wanted to do that. Okay, let's just skip that part for now. Okay, cool. Now, assuming we saw the image, okay, so that first image should look like this. Open a new tab. Okay, that image should look like this. Okay, after training, it should look like this. Okay, this is how my cheat sheet trained. Okay, and you can see here it says now it not only checks stop signs, now it says speed limit. Okay, but you can see there are some errors here. I'll try to. There we go. It says speed limit 100, but it's actually 90. Okay, it's at 0.53, which is 53% of accuracy. Okay, it's like I'm kind of unsure that this is 100 miles per hour. Okay, in this case, you can see it doesn't see 70, it doesn't see 80, it says 60 is 120 and 0.3. Speed limit is 100. You can see that 90 is kind of getting 100. Okay, let's take a look at that in a more fashion way. Okay, so you can do, there's something called, get the confusion matrix. Okay, what is a confusion matrix? plt.imshow, let's take a look at it. plt.imread, and the confusion matrix should be here. See this? Okay, copy the file, paste the file, and voila. Let's get this. Okay, cool. Oof. This is something I don't like to see, okay? Can you see it okay? Is that okay? Or I'll probably do this. Wait a second. Open image in new tab. There we go. Wait a second. There we go. Is that better? I guess that's better. Okay, cool. Now, confusion matrix is no zoom, can't see. Can you see there? Is that better? Oh, that's better. Okay. You can see that, for example, the best outcome. Okay, can see the numbers. Yeah, just look at the colors. Okay, like if I zoom more, even the numbers are a little bit blurry. Okay, and I'll probably do this. Okay, so you can see the colors. The more, like the stronger, or like the more color it has, the more number it has. Okay, cool. So ideally, the confusion matrix doesn't have to have any numbers, but in the diagonal. Okay, what does that mean? It means for every green light predicted, the box points to a green light. Okay, so out of 86 plus 23 plus 13 images with green lights or without green lights, you can see that the green light is confused by a background. Okay, and no, it's not an ident. It's called a confusion matrix because it shows you where the model is getting confused with. Okay, for example, the green light here, it has 86 here. Can you see my, no, can you see my, no, you can't see the, can you see my mouse? You can't see my mouse. Okay, that's weird. Okay, so you can see in the bottom part, or let's take a look at it here. I'm sorry, I thought it looked better. Okay, cool. Can you see my mouse? Yeah, cool. Okay, so you can see that the green lights here, don't see the number, just see the colors, okay? The green light is getting confused with the background. So a lot of green lights, it says, hey, it's a background, it's not a green light. Why does that happen? Okay, so why it's optimal that the numbers are in the diagonal? We'll take a look at this. Green light for a green light. Red light has to be in the red light. So you can see it goes down 1 in diagonal. Speed limit 10, speed limit 10 should go 1 diagonal, okay? So they should meet in the diagonal, okay? So the best outcome is if they meet in every single part, which is diagonally, okay? In this case, it doesn't. You can see green light is getting confused with the background. What's one solution? More epochs, okay? Because it didn't learn anything, okay? We don't have time for more epochs, but it can't see anything. Yeah, it basically can't see anything. You're moving the mouse? Yeah, a little bit. Can you see this? Can you see my mouse? Here. Yeah, you can see it. Yeah. So this green light here, it's getting confused with the background. For example, a red light is getting confused with the background too. That's because we have a lot of, so for each green light or lights, you have some background. YOLO couldn't learn from that, okay? So you can see this is a confusion matrix. You can see the background is getting confused with everything. That's normal, okay? This was going to be a fail because we don't have time for epochs, okay? Let's just play with more stuff, okay? Cool, okay, now let's fine tune for a second thing, okay? Now fine tune. 2. Okay, now we're going to add something called data augmentation. Okay, data augmentation means noising the images. Okay, cool. So how do we do that? So thank God, Ultralytics takes care of that for us. Results2 equals model.train. Okay, now what's the data? The data is actually content, slash content slash car slash data.yml. Okay, same data as we used before. Okay, epochs equals, let's do 2 again because time. Image size equals 640 pixels. Okay, so it's a square. Okay. Name equals fine tune 2. Okay. Yeah, I can see your question. Wait a second. Now, let's add something new. 0.00. Okay. What does this stand for? This stands for the learning rate. Okay. Start. Okay. What happens? YOLO by itself has a learning rate decreaser. Okay, what it does is per each probably 10 epochs, the learning rate goes down 10 times. Okay, so it doesn't, so imagine, so for people who weren't in my past stream, imagine that the learning rate is like accelerating a car. Okay, you say, hey, a bigger or larger learning rate means you train faster. Okay, yes, technically. The thing is, it has to change the weights and the biases. And the weights and the biases are multiplied by this learning rate, okay? So they change 0.001 speed, okay? So it's not a big change, it's a small change. That's why we need more epochs. The thing is, with a smaller learning rate, it takes more time, but it settles in a good number. If we have a very large learning rate, it doesn't settle in any number, right? It just goes like crazy, like 1, 1, 1, 1, 1, 1, and that's too much, okay? So we say, hey, let's just do a learning rate. Let's see if 0.001 works, okay? Why is the background considered an error? Isn't it just noise, which is normal? Okay, yeah. It's considered an error because it does, the box is not, so the box predicted background instead of green light, okay? So it didn't see the green light as the green light, it saw it as the background. And that's understandable because YOLO was trained for red and green lights. The thing is, it wasn't trained, if you see the docs, it wasn't trained enough. Okay, so it was trained like in 1,000 images for people, 2,000 images for cars, in like 30 or 40 images for lights. What does that mean? It means we will underperform for the classes that don't have a lot of images. Okay, cool. And question 2, why increase epochs instead of just telling it to ignore all? Okay, well, that's not good, because let's say that your sign is all white in the background and it just has a number, or the number itself is white. If you ignore that number, then you don't know what the speed is. Okay, so it's not a bad theory. It's just you cannot do that because every single color is data. Okay, if you ignore something, it may lead to data loss. Okay, so never ignore stuff, because in this case, if your number is white, it won't get the speed. Okay, because it say, hey, but I have no speed. But that's not the real world, isn't it? Like, you could do that, but it won't work, right? Like, what happens if, let's say, it should be black and for some reason it has a scratch with which left it white, and you just don't consider that part? Then you cannot ignore things. Like, ignoring things is not good. Okay, it's for, like, you can do it in a way, but it's not real, right? It's a real world in some countries. You know, in my country, which is Mexico, sometimes it's black, sometimes it's, you know, scratched a little bit, sometimes it has a sticker which is white, and you can just ignore that. You have to make sure that the neural network actually learns from that. Okay, yeah, exactly. You don't know, okay, because you don't know, you have to train the model. Okay, cool. Now, HSV H equals 0.015. Okay, that's a number, a random number that I just came up with. HSV stands for hue, saturation, and value. Okay, it's a different way of loading images. Okay, instead of RGB. Okay, just for sake of argument, this is what HSV looks like. Okay, give me a second. Give me a second. Okay, cool. I think this is a good image. New tab. There we go. And wait a second, let me zoom in. Okay. Cool, can you see this? So instead of RGB, we say the hue goes around as a circle, okay, with its hue from white all the way up to blue, okay, or all the way up to green, okay. The saturation is white from, like, the least saturated is the whitest. The more saturated, depending on the hue, it's the color. Okay, and the value goes from black to the color. Okay, it's another way of loading images. Instead of RGB, it's hue. Okay, so in this case over here, you can see we're changing the hue or adding some more hue than it has, 0.015. Okay, so instead of being, hey, it's greenish or it's yellowish, it could be like greenish. Okay, why is that? Because roses or flowers aren't always yellow. Okay, flowers could be all sorts of colors. They can be blue, they can be yellow, they can be green. Yeah, if you train a model that only has white flowers, a blue flower won't be a flower. That's overfitting. Okay, it means you train a model to look at a flower, for example, okay, but it's only blue flowers. So when you say, hey, this is the same flower, it's just green, model would say that's not a flower because you showed me lots of blue flowers that I just think flowers are blue. Okay, that's what we are trying to say, or what we are trying to not achieve. Okay, it means we want to underfit, or we want to underfit the overfit. Okay, we don't want it to overfit. Okay, that's what overfitting means. Okay, how many images do we need to fine tune it on red light, green light? If the model itself was just trained on 40, the more images, the best. Okay, now getting images is not that easy. Okay, you have to build your own data set, you have to build your own data. That's why fine tuning is the best option, because it gives you a chance of only focusing on getting data instead of creating a model plus getting the data, okay, which you have to do. Okay. Another question, when you talk overfitting, what do you mean? Like, yeah, overfitting could be like 1,000 epochs, okay? It looks at the amount of images that you have. Let's say that you have a lot of red cars, for example. And then you say, hey, there's a Porsche, it's yellow. That's not a car because you overfitted the model to see cars as red only. Okay, that's what overfitting means. You don't want to do that. Okay, that's why you have to add noise to it so that it doesn't overfit. Okay, cool. Now that's HSV. So you can see hue, saturation, value. We are changing the hue here. Let's change the saturation too. Like, why not? HSV underscore saturation equals 0.7. Let's just play with saturation a little bit. HSV the value equals, let's do 0.4. Okay, these numbers randomly assigned by me. Okay, you can play with them. Okay, cool. Now it says flip R, flip to the right, okay, by 0.5 or 50%. Okay, because why not? Like, a sign could probably be like moved, or the wind just moved it, or, you know, just to add images to your dataset, you have to do this. Okay, so you don't take a new image, you just create the new image, flip it 180 degrees, you got a new image. Okay, cool. Now, mosaic equals 1.0, which is create from the image a mosaic of the same image. So it actually says or looks at where that thing is. Okay, so you kind of want to confuse your network a little bit so it learns better. Okay, it's like testing your network. Okay, cool. Mix up equals 0.2. So you mix up the pictures a little bit. Degrees, I think it's like rotation. Okay, so degrees, let's add 10 degrees of rotation. Let's just, you can scale the images 0.5. Okay. Translate equals 0.1. It means moving the image. Okay. And shear, which means cutting the image, equals 2.0. Okay. And perspective equals 0.0005. Okay, I'm not sure what perspective is. Forgot about it, but yeah, it works. Okay. Ooh, great, thank you. What it is? What is it? What is it? What is it? Flip R. What did I write? Flip, isn't it? What? Flip R. Flip PLR. Okay. Okay, there's a new one. Thank you. Content card data. Oh, that's the same one, right? The same issue that we had. What's the solution to it? Car. It was training. Oh no, it wasn't training. It was this one. Data YAML. Copy path. Content card. Wasn't it the same? Was I writing cat? What? Is it the same? Data.yml? That I don't know. Okay, that works. If it works, then I'm okay with it. Okay, it's training now with augmented images. Okay, now we added some noise to it. For 2 epochs, we probably won't see that much improvement from number 1. We should see something different. Okay, at least in 2 epochs. Okay, let's give it some time. In the meantime, let's see if now we can get the best weight. Okay. If not, then that's a mystery, because this should work. Like I tested it before. Save, wait. Okay, and then, oh, come on. And then predict using second weights. Okay. Now we do check and see. Predict equals true. So we're going to predict not to see an image. Model equals YOLO with best 2. Image equals this over here, which is content / speed GPT. Okay, hopefully this works. Okay, now it's training. You can see it takes more time because not only it's inputting images, but it's adding noise to them. Okay, so that's mathematically that takes time. Okay, whew, cool. Now let's see. You can see here the box loss is 1.1. Same model. Okay, so we're not training consequently. We're training the same weights and dividing them. Okay, so it's not these weights over here that these don't have anything to do. You can see that the box loss here was actually this is not the one. Yeah, it's the one. 0.7. So you can see that augmentation confuses a little bit the model, but we have to see a big difference. Okay, so 1.1. Oh, we don't see it. Okay, so this doesn't work now. Okay, hey, disclaimer: this wasn't going to work, but more epochs should fix this. Okay, cool. I think. Wait a second. What is your stance using flux? Wait a second. Wait. Okay, what is that using flux Schnell? I'm not sure what flux Schnell is. For example, to generate red light, green light, and training the model on it. Can you explain what flux Schnell is? Never heard of that before. What would the add noise? Okay, here. You can see that we trained, and this is the noise that we added. So HSP, we added some degrees, we mixed it up, we mosaic, we flipped it. Yeah. Okay, so how and where do we add noise? Thanks. Yep, there. I'll still try. Yeah, definitely try. More epochs. 30, 40 epochs should do the trick. It'll take 20, 30 minutes. But yeah. Oh, great. Execution failed. What? What's wrong with my typing today? Is it the... It doesn't work. This is just so weird. It should work though. I'm so sorry about this. The metric noise saved there. See valid attributes below. Okay, let me just Google this pretty quick because I kind of want to see what's going on here. Yeah, you know what? Chat. Good old chat. There you go. Wait a second. Cool. Come on, chat. Load. What's wrong with the internet today? Nothing's with everything's against me today. Okay, so for that specific run, okay, this should have been the output, okay? So this is how it should look, okay? We can see that the speed limit now decreased. It was like 57% of accuracy on this. Now it's 75. It's getting more confused. But you can see that instead of ignoring these two, now ignores the 60. Why? I'm not sure. More epochs should do the trick. You can see that there are some speed limits here. This one, for example, 50, confuses it with 120. This says a lot. Let's take a look at how it's actually looking, or where does the confusion is, okay? So let's just get up here and do the same thing here. Instead of the confusion metric for 1, we'll get it from 2. So fine tune number 2. Ah, what? Fine tune 2. Wait a second, what happened? Fine tune 1, fine tune 1, 2, 1, 3, 2. It's 2, 2. Yeah, it's 2, 2. There. I don't know why it does that. It's kind of weird. Okay. Okay, you can see this. Interestingly enough. Okay. Okay. I'm going to answer those questions. Wait a second. You can see here, just by looking at the image with the colors, you can see that background is winning. Okay. It's not learning that much. Okay. I tried it with 10 epochs. This is how it should look. Okay. See this? This is more natural. You can see that the diagonal makes more sense. Why? Because the green light here, it's getting in with the green light here, okay? And that's good. It says this is the true, how can I say that? This is like the ground, okay? And this is like the predictions. So green light is touching green light, which is okay. 80 images, got it right. You can see that speed limit, we don't have any images. That's interesting. For 100, we get some confusion in 120, which is kind of okay. 47 in 100, which is good. For example, this part over here, you can see that the background is confused by a lot, okay? I cannot see the number. I think this is a 10, yeah? But you can see that speed limit 100 is also confused by the background. Not sure why, okay? You can see the stop sign with the stop sign. It's good, right? It doesn't get confused with other things other than stop sign, which is really good, okay? Cool. Now, this is how it looks with 10 epochs. The same thing that we did with 10 epochs. You can see there the importance of the epochs. Time, okay? But yeah, cool. Now, let's just go back to this one, okay? So you can see a lot of confusion. Again, hence the name confusion matrix, okay? Cool. It's an image generation model. Never heard of it before. But yeah, you can generate the images with generation models, label them, and then create a dataset, okay? I think it should work. Okay, now it costs more money technically because you have to get that subscription or that model for you, and then also training the model, which costs money. Okay, can I print some of the image? So the difference, I can't because of this error, which I don't know what to do. Okay, but yeah, let's just copy the error quickly. Let's see if Chad knows anything about this. Using full analytics, YOLO, I get this. Okay, give me a second. Okay. It's the version of Ultralytics. No. Okay. Okay, matrix. Results model val. Okay, wait a second. What does this mean? Like you can see this. It says results model val. It's the same, right? Matrix, which causes the error. What? It's the same thing. It just changed the name of the variable. What? Okay, yeah, with using Coco, okay. This should work. Save deer. It's the same. What? Isn't it? With let's see what it has to say. Okay. Save deer matrix. Okay, model.val. This just doesn't make sense at all. Okay, I won't go through it more. I'm sorry, I won't be able to show how I'll show you like the cheat sheet one that I previously used. As far as I see, it's the version of Ultralytics that just got released. I don't know when, but yeah, I have to downgrade it. Okay, I won't do that because we have to run everything again. But yeah, okay. Here another question: we're using the same images with and without noise. Yep. So some images get noise, some other not. It's randomly assigned. What's the VRAM required for training this? I got NVIDIA Jetson. Ooh, that's good. I might try it on it. Cool. So VRAM is used so all of the images are loaded into VRAM. Okay, so everything that you have used for training is loaded on RAM and VRAM. Okay, image data will be run on VRAM and image metadata on CPU or like on RAM. Okay, so higher VRAM, it gives the GPU the opportunity to go faster. Okay, cool. Explain the difference between X and Y axis, please. Cool. Okay, so one axis is for the true, or like where the bounding box should be and what label it should have. The other one is the true. Okay, so it says here predicted. You can see here it says predicted. Let's zoom in a little bit more. it says predicted here. Can you see this? I'm not sure. It says predicted and true. Okay, so one is the true value of it, and the other one is just the predicted value. Okay, it basically says here's the error. Okay, that's basically it. Cool. Okay, now running out of time. Let's add noise manually. Okay, that's also fun. Text was too small. Yeah, sorry. Like it says here true and predicted. Okay. By the way, also you have this notebook on GitHub, so if you want to try it, there. Cool. Okay, now let's add dot augmentation ourselves because we see that doesn't work with the ones that we get. Okay, so fine tune 3. Let's add augmentation ourselves. Okay, let's add canny and let's add phrase scale. Cool. Okay, so let's add those two and I'll explain what those are used for. Okay, cool. Why not Gaussian noise, for example? Ooh, that's good. Okay, we could use Gaussian noise. The thing is, it just blurs the image. So if the image was blurred, it'll blur it a lot, or it's like add some noise to it, which instead of highlighting some stuff, we just blur it more. So if the model is poorly doing, because the images weren't that clear at the start, adding more noise in that way doesn't help at all. Okay, but that's a good question though. It's good. We'll add some noise to it, but specific noise so that it helps us. Okay, cool. Now let's do that. Import CV2. Okay. Now image equals CV2 that in read. Okay. Let's add a random image that I chose here because why not? Cool. And now could you sum up which types of noise you see? HSV flipped. Oh yeah. So here they are. I'll go through them again quickly. HSV, you add some more hue to or remove hue to the images. You remove some saturation, some value as well. So you make it dimmer, you make it in a different color, or you put more light to it. Okay. You flip the image, added some mosaic, which basically creates a mosaic of images, and it should have the correct labels. Mix up, so you mix up the images. Degrees, I guess this one, it's like degrees of rotation, as far as I understand. That's the thing. Scale, so you make either the image smaller or bigger, and like the image size stays the same because black pixels are added to it. Okay, we translate the image, so we move the image. Okay, and shear, we crop some part of the image. Okay, perspective, I'm not sure what it is. I guess it's like something that has to do with zoom, something like scale. I'm not sure how it actually works. Okay, cool, nice. Okay, so let's go with let's add some grayscale to it. Okay, grayscale equals CV2 dot CVT color image. Okay, we translate the images, so to color BGR, which is the one that we have, to gray. Okay, cool. Because OpenCV reads the images in BGR, not RGB. Okay, careful there. Okay, cool. Let's add canny. Okay, let's see what canny looks like. Apply canny noise or canny filter. Cool. So it just equals, and you can see by the name, canny allows us to look at the edges. Okay, cv2.canny. I don't remember how, like, what the math behind it works. It's a function, okay, that you just go through it. Okay, and let's keep that number for now, and I'll explain what that number is in plt.imshow edges. Okay, cool. Nothing. Okay, let's add less threshold and let's see what we look. Okay, so from this image that I chose at random, and by random I chose like from 10 the best one to explain this, if you add noise to your images, they could look like this. So you probably, as a human, because you're really smart, you can see, hey, this looks like a 60. Okay. And voila. Okay, let's downsize this. You see, it's a little bit complicated to work with Canny, for example. Either you lose edges or you gain some more edges that you don't want to work with. Okay, and it's basically because Canny is a basic filter. Okay, it's not smart at all, so to speak. Okay, cool. So you can see the 60, yeah. You can see the remains of the whole sign. It's just not good. Okay, if you feed this into the model will say, hey, I don't know what this is. Okay, and that could be happening in your noising. So you have to be careful with the noising. Okay, let's go into, I'll answer the questions in a sec. Let's go into adding Sobel. Okay, Sobel. Sobel is another filter that goes into the X and Y directions. Okay, cv2.sobel, grayscale. cv2 dot cv, oh come on, cv underscore 64f, okay, which is, okay, one, wait a second, I'll explain everything in a second. 0, 1 and 0 means in the X direction, k size equals 7. Okay, this is the kernel size. Okay, same thing for Sobel Y, but it's Y, not X. Okay, there we go. Cool. Now let's do something. Wait a second. Sobel equals cv2.magnitude in Sobel X, Sobel Y. Okay, now we can add some Laplacian. Wait a second. Laplacian equals cv2 dot Laplacian. Yep, with a grayscale. Okay, so no image, like no Sobel image, just a grayscale. Okay, because if not, then you just add filter over filter, and that's not good. Okay, cv2.cv. What's wrong with my typing? What the heck? 64f. Okay. And I'll just copy paste the whole code because I'm running out of time. Okay. I'll just display it. Okay. With imshow. Okay. Cool. So first of all, Sobel. Okay. Let's look at Sobel and how this looks. We'll look at that. So with the same image, this is what Canny does. Okay. Again, Canny is not a complex function. It's just a simple, it enhances doing some math, okay? Magic math. It does some things to the edges. You cannot see the edges really good. I'll answer the questions in a sec, Primatis. Wait a second. You can see that with the same image, we actually see the numbers okay. And you'll say, Eureka, we got it. Like, let's use that one. Let's just take a photo, like a random picture, okay? cv2 in read, it's car valid. We got it from images. Let's take a random image, okay? Blah 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 blah. This one, okay? Copy path. Equals cv2.imread. There we go. Okay. And now let's do grayscale with image number 2. Okay. Cool. Now you can see that Canny does a very, very, very bad job here. Let's see how Sobel works. In this case, you can see that because you're a human, you're really smart. You can see that this is a 30 probably, right? Let's just move the kernel size. If you move it symmetrically, it won't change. Okay, so we can do 3. It has to be odd numbers. Okay, no, so not pair numbers or like not multiple of 2. Okay, Is it odd? I think it's odd. Okay. Yeah, so yeah, it's at 30, but it's just too much noise. Let's do 1 here. Let's see what happens there. Doesn't really change at all. Let's downsize the Y part. That looks a little bit better. Now see, the thing is, we don't have any background here. The backgrounds are probably like a street with the sky. There are no edges. So what happens if we get lots of edges? All of the edges are enhanced. Okay? So when you are noising your image, just be careful to noise them in a way you don't confuse your model. Okay? Because you can use this one, or you can use this one. Canny works good. It's not the best option. You have Stubble too. But you have way better options. Okay? Now, let's see Laplacian. So how does Laplacian look like? With the same image though. Ooh. So Laplacian takes over other, let's do, is it BW? Black and white? How was it? Black and white, was it? No, then I'll just skip black and white. Nope. So it's, what was it? Gray? Gray. Black? Okay, let's do gray. Let's leave it as gray, okay? You can see that it does a good job at getting the circle, okay? It just doesn't do a good job with the numbers. And you might say, hey, cool, let's just pretend this works, okay? Let's just pretend this works, okay? And see, what is this? What did I do here, okay? Probably do a double, okay, cool. Okay, I'll copy this whole thing, okay? Again, you have this on my GitHub. I'll answer the questions. Wait a second. Let me just finish with the code because I'm running out of time. My bad. Wait a second. So basically what this does, it's creating what I'm doing is I'm adding Sobel because it's the one that works the best for now, which was here. Let's just take a look at it again. Sobel. Okay. Yeah, let's just add that to 30% of our images randomly. Okay, cool. So let's do that. In the meantime, while it's doing it, which should be pretty fast, let's check, is it in train? Yeah, in train images. Only training images, not validation images. Validation images are your tests. Okay, if you add noise to your validation images, it's like I'm teaching you how to sum, and then I'm asking you in the test how to divide. Okay, don't do that. Okay, cool. Now, yep, dismiss. Yeah. Cool. Okay, so this doesn't have any, this wasn't the one that got Sobel. Let's just get another one. Let's see if we can get a new one. Come on. Out of 30%, okay? We have to get it. Did I do it correctly? Wait a second. Train images, yep. Okay, cool. Now, oh, cool. You can see that. Now, you can see that probably this image was enhanced good in this part, but not here, right? Okay, that's not that bad, okay? This is probably the one that we're most interested in. And it's actually good. Yep. Okay. Ooh, look at that. So it says stop clearer. Okay, we have a lot of noise here. Yep, we have to just be careful with that, okay? Okay, that stop would have been better if we had like a canny here. I'm sorry, Sobel. Ooh, the 30. Okay, let's take a look at another one. See that? That's a 120, right? Because you're a human and you're smart. AIs are not that smart when they don't learn, okay? 60. Okay, another one with a 50. Okay, and you can actually see the 50 correctly. Okay, so that's a good augmentation. Okay, stop. No. Okay, here it is. You can see that the image or the thing that we are trying to detect is a green light or a red light. You're a human, you know that your red light is here. It's so noisy that it won't detect anything, and this is bad. Okay, that's why you have to be careful with noising images. Okay, cool. I think that's all the code. Okay, in the meantime, while I'll answer the questions, let's train. I have 5 minutes, so I'll add some learning rate. Learning rate final means I want it to go from this learning rate to this one. Okay, cool. Now, and epochs, let's do, let's do 5 epochs. Okay, cool. Let's go. Nice. So new questions. Let me get rid of the cheat sheet. There we go. New questions. Okay. Could you some? Okay, that was answered. Okay, I've gotten some AI image detectors to detect AI generated one as real by adding some noise. I think that's an interesting thing to see how you can break them. Yeah, AI, you can trick AI very easily by adding noise to stuff. The thing is, if you can trick an AI model image detector, you can trick it with simple noise, something that you're training with. You add noise to it, it won't recognize a thing, okay? Because they're learning, okay? It's quite challenging to break a trained model, which is trained on 5,000 or 50,000 real images versus, yeah, it's not that easy. But if you add some noise to it, you flip the image, then the AI could, just get it wrong. And is there any way to extract what the model considers noise versus what it doesn't? Yes. That's a good question. Now, we have to wait until this runs, but here, okay, I'll just show my cheat sheet, which I just closed. Wait a second. Cool that. Okay, I'll show you my cheat sheet, and oh, but wait a second, because I don't know if I have that image on, because I'm not paying for Colab. Ha! Google sponsor me. But I cannot have lots of instances. I could just have one. But okay, I know how. If we go here, you can see, let's just close this thing. Okay, let's go with fine-tune 2.2. Okay, there are curves. Okay, let's take a look at this curve. Okay, can you see this? Wait a second, open HTML tab. There we go. Okay. So these are other metrics, a little bit more complex. Okay, you can see that all of the classes went from confidence, like the confidence went to 1, but the F1, which is a metric in AI, decreased. Okay, so in confidence, like in 100% confidence, the model underperforms. Okay, you can see this. In 0 confidence, it's a great F1, yeah, because the model is getting it wrong. In speed limit 110, okay, so 110 is getting it wrong, and it has F1 in 1. It means in lots of confidence, it's underperforming. Okay? It's like the F value for statistics. Yeah, let me just give you the correct answer, which is, wait a second, let me just ask chat for the correct answer. Wait a second. So the F1 stands for score, harmonic, wait a second. Okay, it's a harmonic mean, okay, between the precision and the recall. Okay, so I think it's precision over recall, something like that. It basically tells you how precise versus how the recall over the confidence here. Okay, so let's just, I'll show you this in a second. Recall, precision. Okay, so lots of people get it wrong. There we go. So this is what I wanted to share. Wait a second. Open image new tab. Okay, so this one. Cool. So false negatives, true positives. Okay. Wait a second. No, this is not the one that I wanted. This is not the one that I wanted. No. Okay. Stay there. Wait a second. There is. Okay. Wait. Recall versus. There you go. There are images here. There's an image that I'm looking at. Here it is. Cool. This is the great explanation of what recall is. Okay. and what precision is. So this is accurate and precise. Okay, this is precision because it's not as this one. Okay, it's like all of the darts are in the same place, but it's not accurate because it's not in the center. Okay, so let's say that it's precision because it says, hey, it's a green light, but it was a red light, or it's a red light, but it's a green light. So it's getting the lights good, it's just not accurate. Okay, or we can get accurate, somewhat accurate, nothing precise, or accurate but not precise. So I'm accurate because I'm saying, hey, it's a stop sign, but it wasn't a stop sign. It probably was a bicycle sign. Okay, but we got the sign part correct. Okay, so we were accurate in that part, but we are not precise because we're getting confused with lots of different classes. Okay, make sense? So that's what the F1 means. It's precision over recall. Okay, and where's the image? Wait a second. 1, 2, 3. Not this one. Should be this one. Okay. Yeah. So this is what this curve is all about. So it has somewhat, again, it's precision over recall. Okay. And in confidence, 100%. There's not even precision nor accuracy. Okay. There's nothing. It's just underperforming so bad. Okay. It needs more epochs. Okay. Okay, what does the stop graph look like when it does a binary? Maybe I'm not sure. But yeah, we have to check. But yeah, that's how it kind of looks. Okay, cool. Okay, so we are looking at that. Okay, so let's just look at the numbers and we'll finish there. It didn't finish training, but you can see class loss went from 2 all the way up until now 1.9. It's not that good. It means our data, as I previously showed, like this one, is confusing the model. Okay, so what does all of this mean? Okay, you have to noise your images in a way that it doesn't confuse the model as much as you want it to. Okay, confuse the model just a teeny tiny bit, so it learns more and it doesn't overfit. Okay. Cool. Now, there are some 5 filters, such as Canny, such as Sobel, such as Laplacian, which are functions that enhance some things. Sobel enhances edges, such as Canny. Okay, careful with that because with this image, you can see it enhanced all of the edges. Okay, cool. It failed. Try it with more epochs. Hopefully some of them will do good. Fair warning, it'll take a lot of time. Okay, but yeah, that's how it looks. That's fine-tuning a model that's not yours, but you're using your data. Okay, so I have a pod meeting now, so I have to go. But yep, I know. Thank you, Slack. But yeah, just please, check in here, and I'll see you tomorrow. I have tomorrow at the same time. Hey, Quakers and Cheese, thank you for staying. Tomorrow, I have one very interesting stream, which is 3D modeling using FreeCAD, okay? So if you want to stay, or if you want to see it, download FreeCAD, which is free. It's like a free version of CATIA, okay? So download that, and you can follow me tomorrow with modeling with 3D, okay? No AI. Us drawing with FreeCAD. Okay, cool. So thank you for staying. I'll go into my meeting, and yeah, please check in. And I think you have Wikipedia races in a second. So by the way, and yeah, Quakers and Cheese, thanks so much. And I'll go to my pod meeting. Bye everyone. Is there a recording yesterday's session? No. Oh, check YouTube. I think it's on YouTube, not on Twitch, on YouTube. Thank you for staying, and bye bye. See ya.